Hello everyone, this is Shahid Qureshi along with my teammate Jinish. Today we'll be giving you a demonstration of our final project, that is implementation of image warping algorithm, and we have used Altera DE1 board for it. We have implemented this algorithm using Matlab, C programming and Quartus, so we'll be covering a demonstration for all of these. So let's proceed to the Matlab implementation of the code. So this is we have read an image of size 512 cross 512. Then we have resized it to 128 cross 128 so that there are fewer pixels. Now we have implemented this algorithm using backward mapping. There are two techniques: forward mapping and backward mapping. Backward mapping eliminates holes in the output image, so that is why we have chosen backward mapping. This is the affine transform that we have done on the input image. We have done a rotation of 5 degrees on the input image, so you can also perform translation. Scaling can be just done by changing the affine transformation matrix. These are the coefficients that will be needed for bilinear interpolation. There are inbuilt functions for seal and floor in Matlab. Using those, we have calculated the coefficients needed for bilinear interpolation. These are the conditions we have given for the pixel which become negative. Now there is a possibility that the new pixels uh, may become negative. If they become negative, we need to put conditions for them. So these are the conditions that we have given. We have avoided the image input pixels that become negative, otherwise Matlab would give an error. So let's go ahead and run this code. So this is the input image that we had read, and this is the output image on which we performed 5 degrees of rotation. So this is the Matlab implementation. Now we'll proceed to the implementation of this algorithm in C. Now this is the C implementation of the code. There is not much difference between the Matlab code and the C code. Matlab can directly read an image using imRead function, but in C code we have to specify all the pixel values into an image array. This is the same image. We obtained this image from Matlab. J2 was the input image, so you can directly access the pixel values from this matrix. This matrix is copied into C. This is the input matrix. This is the output image. We have added the first row with 0. Since we are starting the image, we are starting the loop from 1. Loop goes from 1 to 128. This is the same as I explained. The affine transform, the coefficient for bilinear interpolation. These are the conditions for pixel coordinates that become negative. This is a code for generating a .csv file. The output of the image will be stored into a matrix. The pixel values from this matrix will be copied into a .csv file. So this matrix can be directly used into Matlab to display the result. So let's go ahead and run this code. So let's enter the name of the .csv file. This is the output. this is directly copied into the .csv file. So we have used this in Excel. There is the .csv file. So we have copied it into Matlab. This is the output that was generated by C. So we have just initialized it to a matrix and then changed it to uint8 format, using which we can display the image. So let's go ahead and run it. So this is the output we have obtained after running the C code. So that was the Matlab and C code implementation. So now we'll be proceeding to the implementation in Quartus using Neos 2 and Qsys tools, which are already there in Quartus. We'll be using hardware accelerators in that. So Jinish will be explaining the next part.
Hello guys, I am Jinish Shah, and so now as you saw that how we implemented the algorithm in Matlab and C, now we will proceed to how we will be doing it in Quartus 2. That is, now we'll go to the hardware approach. I'll just open the Quartus software. So let's make a new project. And give it a directory. Let's name it final project. Now I don't have any files right now, so I won't add anything. We are using the Cyclone 2 board, and we are using Cyclone 2. We are using DE1 board, which has Cyclone 2 device on it, and the device family that we are using is this. We need to run our simulation, and our new project is created. Now I need to build a SOPC system in Qsys. So let's launch Qsys. Here in Qsys you need to add the components that you are using on your FPGA, which will generate a SOPC file, which is then implemented further. So actually in this process, for implementing this algorithm, I'll need 3 hardware accelerators. So those are the 3 user defined components we can define over here. So let's add one by one. I'm adding the first component. We have to add our files over here. My first file will analyze and synthesize. Okay, so now we are good to move ahead. The signals, these are the signals like reset, clock, read data, write data, and address. We are following our Avalon memory access protocol over here. Now the interfaces, we need to provide the associated clock and the associated reset. And now our first component is created. Let's create our second component. This is my second component that I am preparing. The procedure remains again the same. So here actually I will include two models because I am also using inbuilt multiplier module of Altera. So these are the two files that I will upload. My mapping.p is my top level entity. So if like you can assign whatever top level entities you want to from here. This is my top level entity. We will again analyze these files. This process remains same. Every time I need to add a custom component like this, the files, the signals, again giving associated clock and the reset and saving. And let's add my final component. In this component also I'll be using two files, that is mapping1 and mult1. This is my top level entity, mapping1. Now I will proceed by adding Neos 2 processor that we will be using. We will use the economical version. We will also need some on-chip memory. Now let's add some on-chip memory. Actually, for on-chip memory, we have very limited memory on our DE1 board FPGA. So it is like say 20,480 bytes. We need more and more memory for this algorithm to be implemented. Like say if our resolution is more, we will need more memory. But this is the limit amount of memory available, and so that's why we will be implementing this algorithm for a smaller image size. Now let's add some JTAG UART. Now one by one I'll be adding my hardware accelerators components. Mapping and then mapping 1. Now let's interconnect these components and let us connect the interrupt. Now let's provide the base address. Okay, so this provides the base address is right over here. Now we need to provide on-chip memory address to our Neos 2 processor, which will remove all the warnings that we have. And now we are good to generate our file. Make sure that you name the file over here same as our project name. This is generating, so all our files are now generated. Now let's move towards project. Let's add our files over here. So basically I can add just one file, that is .q. It will be in it is IP variation file, and my each and every file will be added along with it. And give clock. Location and which type of input output standard it follows. So my clock, machine clock represents pin L1 and it is of this input output standard. Let's save our assignments. Now we are good to compile our project. Okay, so it seems that our program has been compiled. Here are all the design units. My hardware accelerator components. So this is the first component, hardware accelerator. Now this component is basically used for matrix multiplication. These are all the signals input output that I have given over here. Now this A and B, I need to multiply it with my matrix contains cos 5, sin 5, minus sin 5 and cos 5. So I have created A as 127, which is cos 5, which is approximately equals to 0.99. And so when 0.99 we convert it in binary and then to decimal, we will have this values, and same like sin 5. So whenever we divide 11 divided by 128, we will get the value of sin 5. Likewise, for when we divide 127 by 128, we will get the value of cos 5. This is basically 8-bit signed values. Now this is the output that I am giving, the transformed values of my coordinates to the output. Now here this is basically what I do in this hardware accelerator. This is matrix multiplication and then they are added. This was my first hardware accelerator component. Now let's move forward towards mapping. So in this mapping, what I do is that in this mapping, what I do is actually I follow this part of our algorithm of the functions, the 1 minus h, 1 minus k, and h into 1 minus k, 1 minus h into k, and h into k. This is the interpolation algorithm that we are following. And so here I do 4 matrix multiplication of these 4 values. Right over here, and for that I use this mult, which is inbuilt multiplier of Quartus 2. And here, as my values now exceed the more than what I want, so here I perform rounding. This is the rounding algorithm. Now this here the bits are given to the output, and this is the complete implementation of that function. Now let's move forward to our third hardware accelerator, that is mapping 1. In mapping 1, I follow this part of the algorithm, that is in mapping I calculated this this and this, and now it is time to multiply all of these together. So here P00, P10, P01 and P11 are my pixel values at different locations. P00 are the location at ceiling, floor of X and Y. P10 are at X at ceiling, Y at floor, Likewise for P01 and P11. So here I have 8 inputs, multiply them respectively, again round them and send them at the output. Here I have implemented rounding twice, and so my quantization error has increased. But this is what is necessary, because as we don't have floating point arithmetic in hardware, that's why we need to do rounding and saturation every time. And that's why, as I did it a couple of times, my quantization error has increased a little bit. So now let's proceed towards programming our FPGA by dumping our file. So let us add our .sof file that has been generated upon compilation. So you can see our device has been 100% successfully dumped. Okay, so now here the Quartus part ends, and let's move towards the Eclipse. Let's create a new project. We will use the inbuilt template that has been provided in Neos 2. Eclipse. This is the SOPC info file that will load, which actually gives the information of all the interconnected components. Let's name our project. We will use hello world small template. As you can see that this is displayed. Now let us put our own program in here. So this is our C program, and these are all the pixel values that we have added over here. This is for, unfortunately, for 32 cross 32 image size, because of our limited on-chip memory that we can use over here. This is our image that is declared. These are the pixel values that we are generating at each time. Now these pixel values will go in our hardware acceleration module, that is the first module, and the matrix multiplied output will give us new coordinates x1 and y1. Now this is the floor function and the ceiling function that we'll be implementing over here. So x floor is basically x1 divided by 128. Remember that we are now x floor is an integer, there is no floating point implementation. So whenever we divide it by 128, it will be by default give us x floor and y floor function. And now corresponding ceiling function will be, we will be just adding 1 to it to make it a ceiling function, because again we don't have any floating point. So now here h and k. H is actually our algorithm. It is 1 minus h and 1 minus k over here, and for h and k it is generally based on the ceiling and the floor function. Here my h and k are calculated in this fashion, because actually my h is x, that is the original value, minus the floor function of x, and k is the original value of y minus the floor of y. But here basically my transform like x and y values will be in decimal in floating point, but here we don't have that kind of architecture. That's why what I found out was by implementing this x1 minus 128 into x floor. So that would be because my x1 is already multiplied by 128, and my new h and new k I calculate in this fashion. It is generally 1 minus h, but like It is now, as I am multiplying everything by 128, so this is what I have done. Now this is the writing. These all values will go to the second module, that is the mapping, and it will give me the output. It basically, that output is the multiplication of new h, new k, h, new k, k, new h, and h and k respectively. All the four values are now going in the multiplication with p00, p10, p01, and p11. So these are p11, these are my values at different ceiling and floor functions respectively. So in my algorithm, so here in my algorithm I'll pass this values pq, rq, ps, and rs, from which I have generated right over here my pixel values. So here the interpolation occurs, and I will get four outputs, that is uv1, uv2, uv3, and uv4. Now all this I will add them to find the final value of my new pixel, and for new location also. So now again, if they are the summation, due to, as I told you earlier, that I have approximation, and so they generally sometimes go over to 55, which is not possible for a gray image. So due to that error, if they go above 255, I will declare them as 0. Otherwise they will be the addition. Now again, here this part I have written to see them in a form of a matrix at the output of my C code. So this is generally because, like, j is equal to 30, so whenever my row is completed, so it will, for columns it will go with this, it will do tab, and for rows it will take a next line. So now let's implement our this algorithm over here. Now these are the base addresses that I have given. Let's see whether they are correct or not. So for hardware accelerator we have 11800, 11400, and 11000. So I'll just arrange them. Here's my whole program. Let's build our program. It is built. Now let us run. Here's news to hardware. Okay, so here are all the values that we have, and we can verify them in the Matlab, and the answers, as I have approximated it twice, so they are like really approximated values, and so we have successfully implemented the algorithm. Thank you. So if you have any doubt, just comment.